In this video, I want to go over Earth's Milankovitch cycles, which are natural cycles in Earth's climate, where they come from, and the sort of periods that you get. And also, can these cycles relate to other objects, not just the Earth? Well, let's first start with Earth's orbit. Now, we assume that it is always the same, it doesn't really change, but it's also one of the defining features that drives the climate. So if we move further away, obviously going to decrease the amount of energy falling on the Earth, we get cooler. But we assume that it doesn't necessarily change. The Earth is pretty much on its orbit around the Sun, and that's that. We don't really think much more of that. But if we look at the actual climate in the past of Earth, we can see that it's gone through cycles of ice ages and then periods in between. And they're not just random, they don't just randomly occur. When you look at it on a plot, there's almost a cycle to it, so there's a set period in between each one. How do we know that? Well, if you have a look at ice cores and deep sea sediment cores, so this is where you would take a really deep, basically a sample through the sediment or through the ice, and then you can look at the actual temperature of the Earth over a long period of time, so hundreds of thousands of years, and you can find out how the climate is changing as a result of that. And when you create a plot, you can look at the temperature. So the middle line here, the black line, is the temperature anomaly at Antarctica. And you can see that it's increasing and then decreasing. And then you've got the carbon dioxide at the top and the methane at the bottom. Now, the important thing here actually is that we probably think that carbon dioxide is the driving force of temperature, but in these results here, it actually lags the temperature. So it's not the cause of the change in temperature, it actually just increases, maybe because the temperature is increased. It's not the other way around, which is important actually. So something's causing those changes in temperature, either to increase or decrease. Now we know that Earth's orbit can dictate what the temperature and climate is. So it could be that there are orbital changes that are occurring, that are cycling, which then drive the changes in the climate that we are actually measuring in the records. So the first one relates to how elliptical the orbit is for Earth. So what happens here is the Earth's orbit becomes more elliptical and then less elliptical, and that cycles around about every 100,000 years. Now, what that does to the climate is it's going to make your seasons more extreme, because for some part of the orbit it's going to be closer to the sun, and then other parts will be much further away. Whereas when it becomes more circular, then the seasons are a bit more stable, or they're not that different. So you're not changing the distance from the sun much if it's circular. Now the second one then relates to the tilt of Earth, or the angle of Earth's tilt. So it cycles between 22.1 and 24.5 degrees about every 41,000 years. And again, this can make your seasons more extreme because it tilts over more. And it's actually this tilt that gives us our seasons. If we had no tilt at all, we'd get the same amount kind of all the way through one orbit. But this actually will change what happens in your season, stuff like that. It happens about once every 41,000 years. You then also have precession. So again, that rotation axis of the Earth, you can see with the red line there, it actually precesses. So actually it makes this kind of circle out. And that does that about every 25,000 years, or well, just under 26,000 actually years it takes to do one of those cycles where it precesses about. That's the rotation axis. Now what that does is it's going to change the start of your seasons, and it can also create a larger difference in the temperature between each hemisphere. So northern hemisphere, you're going to get larger differences in the total temperatures, or the energies falling there as well. Now, it's worth noting that a spinning top like this here, as it begins to slow down, it also begins to wobble. So that rotation axis is vertical, but as it slows down, it wobbles a bit. And you can see the angle changes, and it also will be precessing as well if we look top down onto it. And the same thing is happening with the Earth here. So it's actually wobbling on its rotation axis, which is one of these cycles. Now, the other precession one is to do with the orbit itself. So the orbit is elliptical, and the actual orbit itself, so that elliptical orbit then precesses around the sun. And that can take about 112,000 years to do one full cycle. And then the final one is inclination. So if we were to look edge on at the orbit, The inclination is how inclined it is from the normal orbital plane. So most of the planets are orbiting in a common plane, but they have some inclination to that, so that they come out vertically. And that inclination for the Earth cycles about every 100,000 years. So similar to how elliptical the orbit becomes and less. Same sort of time period, actually. Now, the interesting thing here is that the inclination and the eccentricity periods are about 100,000 years. Now, that matches the glacial cycles. So that matches the cycle that we measure on the planet in the records from the ice cores and things like that. So these two things relate to that, which is interesting. Now, what's actually driving these cycles? Well, interactions with other planets. So Jupiter and Saturn are quite large planets in our system. As they pass by, they exert a gravitational tug, and it's interactions like that that they can drive these cycles. So interaction with other planets, basically in the same system. You get similar sorts of things happening with the tides from the moon and the sun. So the moon and the sun both have a gravitational force exerted on the Earth, and they essentially tug on it. And those can also drive some of these cycles as well. But Earth's not the only one that undergoes these sorts of cycles. So Mars also has Milankovitch cycles, and these can range from about 50,000 years up to 1,000,000 years. And again, the tilt, how elliptical the orbit is, and the inclination all show these sorts of cycles. They're slightly different to Earth, and the amplitudes are different as well. So they can actually be a bit stronger than what Earth is experiencing, but they do undergo similar sorts of cycles that Earth does. And it's not just planets, even moons can undergo these sorts of cycles. So Triton, which is Saturn's moon, and it's quite a significant moon which has an atmosphere. It also has methane lakes on its surface, which you can see there from a nice Cassini image. Now, 60-year cycles on Triton could actually change the location of those methane lakes. Because, again, if you're changing the climate on the moon, its temperature, how that temperature is distributed on the actual moon, then those liquid methane lakes are going to change their location over this period of 60,000 years. And Neptune's moon Triton, which is actually almost comparable to Pluto, it's just a captured moon, could also undergo similar migration of nitrogen deposits on its surface due to similar cycles to what Triton has. So it's not just Earth that undergoes these cycles. A variety of objects, big and small, can undergo these similar sorts of cycles in their orbit, which would then impact their climate or their temperature. So thank you for watching, and if you enjoy, check out some of the other videos.